All right, we are live now, and we will begin with week 3, and then we will move to week 4. Okay. Yes, Komali, what is the doubt? That we will see, no? It's week 6 related thing, no? So let's focus on week 1 to 4 for now. And so the syllabus for our exam is week 1 to 4. Okay. So no week 5. Right? Uh, any questions before we begin? So week 1 and 2 we have already revised yesterday, and links are available in the calendar also. Okay, so you can open the calendar and go to the previous yesterday's session, and you can click, you will get the link. Okay, and today we will revise week 3 and 4. Okay, so let's begin. So we are already delayed by 5-6 minutes. All right, so we all know sequence is basically a function that maps the set of natural numbers to set of real numbers, and a sequence is nothing but an arrangement of numbers, right? So there will be a first number, second number, third number, fourth number, and so on, right? So in the same way, examples are like a toy example is an is equals to n, where I start my sequence with 0, 1, and the next number is 2, 3, and so on, right? So, and there are many other examples. So if an is minus 1 whole power n, then my first number is minus 1 power 0. So usually, sometimes we start with 0, or most of the times if we don't specify, it implies that it starts with 1. Okay, so the first term is a1. Okay, so here in the lectures we have said we start with a0, but most of the examples that we dealt in practice or graded, even in exams, we will specify where to start, but if we didn't specify anything, it implies that you should start from 1. Okay, so you should consider from n is equals to 1, 2, 3, and so on. All right, and the general representation or denotion of a sequence is like this, right? So we denote a sequence like this, right? So where an, the inside the curly braces, an denotes the nth term of the sequence, right? So this is one way of denoting a sequence. When we say a sequence within the third bracket an, it implies that we are talking about a sequence, not just a number. I hope most of you know that, right? So when we say a sequence n, it is not just n, right? So this is actually, if I write this explicitly, this means this is 1, 2, 3, 4, 5, 6, and so on, right? So it's a sequence, and I felt this is worth mentioning here. Okay, so most of your previous batchmates thought this is like n is given within some third brackets. Okay, so I hope you guys know that. And another way of representing sequence is by giving it in the form of recursion relation, right? So something like, we'll give you some terms, first one term or two terms like this, and then we will give the relationship between the current term and the previous term, or current term and previous term and the previous to previous term. Okay, so there is a relation given to us which connects the current term and the previous term. So these kind of sequences are dependent on their previous terms, right? So if I write this sequence explicitly, this is how it will look, right? So the first term will be 0, the second term will be 1. These two things are given to us. For getting the third term, we have to use this relation, this formula. So if I substitute n is equals to 2, right? N is equals to 1 here. Okay, so if I substitute n is equals to 1, I will get a2, which is the next term. For a2, all I have to do is a1 plus a0. So that means I have to add these two things to get the third term. For getting the fourth term, I have to add these two things. I'll get the fourth term. So recursion, giving it in the form of recursion relation also is one way of representing a sequence, right? So we know arithmetic progression, which connects with previous term and the current term, right? Uh, and the geometric progression also we know. So there are multiple sequences which we have already studied, but we don't know that these can be kept as a sequence or represented as a sequences, right? So all these things we have learned in the lectures also, and that is denoting or representing sequences. And how do I visualize sequences? The best way to visualize sequences is through stem plots. Again, what is stem plots again? Stem plots, where it's also has some axis, x-axis and y-axis, where x-axis has only the natural numbers, right? So it starts from 1 or 0. Again, it is just the notation, okay? So either you start from 0 or 1, it doesn't matter. So our first term is 0 here, okay? And x-axis will only contain 0, 1, 2, 3 and so on. And then y-axis contains uh, the real axis. And what does this stems mean is, at each point like 0, 1, 2, 3, I will plot a stem like a straight line, and the height of that straight line is actually equals to the value of that particular term. So this is a0, this is a1, this is a2, this is a3, a4, a5. Okay, so on the y-axis we will plot an, on the x-axis we will plot n. Okay, so this sequence is nothing but an is equals to n, at 0, 1, 2, 3, 4. So the stem height will increase as I progress in my sequence, right? When an is minus 1 power n, it at 0 it takes value 1, at 1 it takes value minus 1. So the stem height goes below, stem goes below, denoting it is a negative value. Okay, if it is positive, stem goes above x-axis. If it is negative, stem goes below x-axis. All right, so here there are many examples and their stem plots, and this is best way to visualize sequences. Okay, and proceeding. So once we understood about the sequences and how the sequences are denoted and how they are visualized, the next thing that we study is the properties of the sequences. And there are two main important properties. One is boundedness. I think in week 3 we have discussed this explicitly.
Yes.
Let's quickly go through this again. And the other one is monotonicity. Right. So these are the two important properties of the sequences. So when I say boundedness, we are going to compute the lower limit, right? Upper limit. So all these things come here. Upper limit. Then we talk about bounded above, bounded below, right? So bounded and then unbounded. So all these terms comes in this concept of boundedness. And then monotonicity is basically we'll talk about the sequence, whether the sequence terms are increasing or decreasing. decreasing, right? So these are the things. So let's go through them very quickly. So what does bounded above, bounded below, or unbounded sequences mean? Yes. Okay, so a sequence, again, see here, you can see it clearly, right? A sequence within the brackets an means this is sequence is bounded above, right, or upper bounded. So you can call it any way. We usually use this bounded above term most of the time, right? So it is bounded above by some real number capital M if all our sequence terms are below this M. Okay. So for all n, if my all my term values in my sequence are lesser than or equals to this capital M, where capital M is a real number. Okay, so this capital number can be any real number, real constant number. Okay, so it's a constant real number. So if I can find this capital M such that all my term sequences are lesser than this M, so that means all my terms are not going above that particular capital M. Therefore, since it is not going above, it is bounded above. Okay, so that is bounded above means. And again, contrarily, bounded below means all my sequence terms are greater than or equals to some real number small m. So again, this is also a constant real number. Okay, so if all my term values in my sequence are greater than or equals to capital M, that means none of my terms are going below this small m. Therefore, my sequence is bounded below. Okay, so there is a real number that is below to my sequence such that none of my terms go below. So that is why it is called bounded below if there exists any small m. And this capital M and small m are called upper bound and the lower bound. Okay, so this capital M is called as upper bound. Okay, and the small m is called as lower bound. Okay, so there are examples again. So let's not pick the first two. First two are really easy. So let's do the third one. If you see an is 1 by n plus 1, you will see that when you substitute n is equals to 0, it will give you 1. When you substitute n is equals to 1, it will give you half, 1 by 3, 1 by 4, and so on. So now we can see here that by looking here, you are seeing that as I progress, it will just become closer and closer to 0. But none of my terms are negative, right? So 1 by n plus 1 will never be negative because 1, the numerator is not negative, n is not negative, 1 is also not negative. So positive by positive will always give me a positive value, right? So once I can see that, then I can guaranteely say that all my terms are greater than 0, right? So it may be equals to 0, we don't know that, but at least I can tell that none of my terms go below 0. So therefore, we can say that there exists a lower bound and 0 is actually a lower bound for this particular sequence. And there also exists an upper bound for this particular sequence, right? None of my terms go above 1, right? So for the first term is 1, which is equals to 1. But later, if you see the second term, third term, fourth term, and so on, none of your terms actually go above 1. So therefore, all my terms in the sequence are lesser than or equals to 1. So only the first term is equals to 1. None of other terms are all less than 1. So therefore, there exists a capital M, which is 1, right, which actually bounds from the above. All right, so there exists an upper bound for this particular sequence also. And again, the best way to understand it is through plots, right? So visualizing through stem plots. So if I just plot this, okay, so let's say this is 0, this is 1, This is 2, 3, 4, 5, 6, 7, 8. Okay, and so on, but we'll just stick to it. And these are an terms. Here we are considering an to be 1 by n plus 1, right? So now at 0, n is equals to 0, this will be equals to 1. Therefore, the height of the stem will exactly be 1. Okay, and we will put a solid dot mentioning that the height is ended at that point. Okay, and the next term, when n is 1, it will just be half. At n is equals to 2, it is 1 by 3. At n is equals to 3, it is 1 by 4, 1 by 5, 1 by 6. Okay. At 7 itself, it is very 1 by 7 itself is very close to 0. And we can see that, right? So now what this upper bound is, if you can draw a line, horizontal line, right? If you draw a horizontal line, if you can draw one horizontal line such that none of your terms go or intersect that particular horizontal line. Okay, so intersection means none of your stems actually cuts or goes above that line. So if you can find that line, then that line value or that equation value, this one, will act as an upper bound. So this is like upper. So from the upside, you are just blocking it. You are just blocking the sequence terms. None of your terms go above that. Okay. So here in this case, I can actually pick this line to be exactly equals to 1. Right. So there is no harm in picking this line. None of my stems actually go above that line. Right. So above that green line. So therefore, this is an upper bound. Similarly, I can get a lower bound in the same fashion. Right. So if I can draw a horizontal line such that none of my stems actually go below that line, right? Here in this case, I can actually take this x-axis itself, right? So this itself, because I know that none of my terms go below this line. Therefore, 0 acts as a lower bound. So all my sequence or the stems will lie within these two lines, within these two green lines, green horizontal lines. So in that way, you can visualize, right? So this is what boundedness means. Okay, so when do I say a sequence is bounded? So bounded sequence means when it is bounded above as well as bounded below. Okay, so I need to have boundedness in both sides, above and below. Only then such sequences are called bounded sequences. If I have only bounded above and the sequence is not bounding below, or if it is bounded below and if it is not bounding above, or if it is not bounding above, not bounding below, such sequences are called unbounded sequences. So unbounded means any sequence that is not bounded. Right? So if it doesn't fall in the first category, it will fall into the second category. So the second category is unbounded sequences. Okay. So here also you can see some examples where lower bound exists, but upper bound won't exist. Upper bound exists, lower bound won't exist. Right. So these are the two examples you can see. One first example, you can see that there exists a lower bound, but there is no upper bound. So you cannot bound from the above. Therefore, this sequence is unbounded. Right. So this is unbounded. In the second example, you can see there is a lower bound, there is also an upper bound. This sequence is bounded. Here also, third example also, just now we saw it's a bounded because it is bounded above plus bounded below also. In the fourth example, you can see there is no lower bound, but there exists an upper bound, which is -1. So again, this is unbounded. And here in the final case, you can see there is no lower bound, there is no upper bound also, which will make it again a unbounded sequence. Okay. So when I say when we say bounded and didn't mention whether it is above or below, it is both. Right. You have to check for both. When we say bounded above and bounded below specifically, then you have to just check for bounded above and bounded below. All right. So there are more examples also. Go look into this. These examples are given in the form of recursions. Right. So here also you can find a lower bound, upper bound, and see if both lower bound and upper bound exist, only then the sequence is bounded. Okay. All right. So solve some more examples related to these properties. Now coming to the next property, which is increasing or decreasing, and non-decreasing and non-increasing also we have discussed this, right? So just go back to the earlier sessions. I don't want to spend too much time on what is the difference between increasing and non-decreasing. Okay, so if you want that, you go back to the earlier sessions and watch it. But here it is very, you can again refresh your knowledge on this increasing and non-decreasing. Okay, so a sequence AN is called an increasing sequence when my next term is greater than the current. Okay, so as n increases, in very simple words, as n increases, if an also increases, then it's an increasing sequence. Okay, what is non-decreasing means? Non-decreasing means it may increase or it can be equal to also. So it can stay the same value. Okay, so that is non-decreasing mean. So there is some relaxation for increasingness that we are going to provide so that that sequence is called as a non-decreasing. Okay, so there is a slight difference. You just have to understand it. That's it. So there is an equal to coming here, right? So that means so there is some relaxation in comparison with the next term and the current term. Okay, so that is non-decreasing. Mostly increasing is much sufficient for us. So if you understand increasing, don't bother about non-decreasing. Okay, so now what decreasing? How does the decreasing sequence look? As n increases, my term value should decrease. Right, so an should decrease. So that means if I look at the sequence, the next sequence, the next term in the sequence should be lesser than the current term. Okay. So here again there are examples. An is equals to n is a very toy example. Again, it's just 0, 1, 2, 3, 4, and so on. You can see here clearly that as n increases, my term value also getting increased. An is also increasing. So it's an increasing sequence. An being oscillation between two numbers, 1 and -1. You can see that as n increases, here it is decreasing and then increasing, decreasing. So there is no proper relationship between an plus 1 and an minus 1. An, right? So sometimes an plus 1 is greater than an, and for some different an plus 1 is less than an. So here for all n is really important. So this condition should hold for any n. Okay. So oscillating sequences are neither increasing nor decreasing. So it's none or neither increasing nor decreasing, we say. Okay. And the example that we saw, 1, 1 by 2, 1 by 3, 1 by 4, and so on. So it's a sequence where as n increases, my term values a n are decreasing. Therefore, it's a decreasing sequence. Even minus 2 power n is like minus 1, minus 2, minus 4, minus 8, and so on. Right? So as n increases, my a n is decreasing. It's a decreasing. Now again, it is like oscillating between positive and negative values. Here you can see 1, minus 2, 4, minus 8. So you see 1 is greater than minus 2, but minus 2 is less than 4. 4 again is greater than minus 8, right? So minus 8, and again minus 8 is less than. So there is a greater than, less than, greater than, less than kind of sequence. So it is neither increasing nor decreasing, right? So that is why it is shown as none. Okay. So here again, these are the examples with respect to recursive relation. Okay. Any doubts
Sir,
so far? Yeah.
uh, in the in a question I want to ask,
What do you want to ask?
sir, a statement given in the question one, week third question. May I speak,
Okay.
sir?
Okay. Is it related to this particular concept?
Yes, sir. Yes, sir.
Okay. So
Sir,
week
first
three.
week three, sir. AQ 3.8 activity question, sir.
Uh-huh.
Sir, a statement is a non-decreasing sequence that is bounded above has a limit.
AQ three
Non,
point. Can you tell me which activity is it?
uh, 8 activity, sir. 3.8 activity question.
3.8.
Yes, sir.
Okay. So this is
First question.
okay. So we'll come to that. That is MCT, no?
Yes, sir.
Mm-hmm. We didn't come there yet, right? So we'll come there. So as of now, we just discussed what is a sequence and properties of sequence. So 3.8,
Okay.
I will discuss it when we talk about monotone convergence theorem, which is
Okay, sir.
MCT. Okay. Yeah.
Sir,
Okay, sir.
sir, I have a doubt.
Hmm.
So, what is the meaning of recursion form?
Sorry.
Recursion, recursion form.
So recursion means the next terms are dependent on the previous terms.
Oh,
So that the
okay.
sequence is recursively formed by using the current terms.
Ah,
Okay. So that is why it is called recursion relation.
the following term comes from the previous term.
Previous term or previous two terms.
Okay, okay. Thank you.
Yeah.
I got it.
Yeah. All right. So any other doubt? So where from we define the root to sequence? So what does that mean? Where did we get this root to sequence is the question, is it?
Yes, sir.
Okay. So root to sequence, it is named as root to sequence because the limit of this particular sequence goes to root 2. Okay. So it came from uh, early 1700s or 1600s, I guess. Okay. Some mathematician has given this particular form, and they define that rational sequences can converge to irrational numbers. So from there, they kind of came up with this kind of expression and shown proven that the irrational numbers do exist, and they can be, and yeah, they can be the limits of some rational sequences. Okay, I don't think that is right now that is necessary. Okay, but understand that sequences can also be defined as in the form of recursive relation, and this is one sequence where it is represented as in the form of recursion relation. Okay, all right, so let's proceed. Let's talk about limit of a sequence. Okay, so limit, now coming to the limit of a sequence, here I think this is too overwhelming to see this L minus epsilon. Whenever epsilon comes in, no, we will lose interest in math, right? So it feels like that, right? But let me give you a simple understanding of what this limit of a sequence mean is. Okay, so as n increase, okay, as I progress along my sequence, and n becomes very large. Okay, so we can't even imagine. So we'll start from first term, second term, third term, fourth term, and once you reach 100th term, it feels like 100 terms you have observed, right? So then when you reach 1000 term, a 1000, so you will look at a 1000, right? And as n increases, still from 1000, if it still increases, what is happening to my sequence terms? So that's the question. Okay, so as n goes very large, do my sequence terms come to a single value, or is it going to somewhere else? Okay, so if it is coming to a single real value, then what is that real value, right? So that real value is nothing but the limit of a sequence. Okay, so you can see from this stem plots, right? So initially our sequence terms are oscillating, right? So the first term is here, second term is here, third term is here, fourth term is here, fifth term, sixth term, seventh term, eighth term, ninth term, and so on. But as you see, as n goes to 40, you will see that our sequence terms are like this, right? As n became 80, you can see this sequence terms are very close. As n became 100, you can see almost the same value, right? So as you go, n becomes 1000. Maybe if you drag this and if you see at 1000, it will be like this, right? So there will be a very little difference. So which implies that at 1000 itself, my sequence values are all becoming the same, and that is actually equals to this L. So this height L, okay, which is 0.5 in this case. Okay, so if at all my sequence is behaving like this, such sequences are called convergent sequences. Okay, so again I will repeat. So sequences in which as n becomes very large, if my term values are also becoming a single real constant value, such sequences are called convergent sequences. Converge. So this converge means everything is coming together and becoming equal. Okay, so the later terms are all being equals to L, almost equals to L, right? So such sequences are called convergent sequences, and whatever this later terms takes the value, okay, so this L, okay, so that L is called as the limit of the sequence. Okay, so that's it. So this is what a limit of a sequence is. So what I do is I take the expression of an in terms of n, and I see as n tends to infinite, what is happening to this? Is it actually equals to some real number L, or is it going to plus infinite or minus infinite, or sometimes we cannot judge. some terms will go to some value, some other terms will go to some other value, right? So we cannot judge in that condition. So we saw that example also, right? We'll see some examples to get.
Excuse me.
Yes.
Sir,
Hmm.
sir, I couldn't understand the concept here. Can I have this? Sir, can you repeat it?
Okay. So what do I mean by limit of a sequence means is, so for example, okay, I will take an example and then it will be clear. Okay. Hmm. So the example that we are going to take again is this 1 half, 1 by 3, 1 by 4, 1 by 5, and so on. Right? So these are the 1 half, 1 by 3, 1 by 4, 1 by 5 are the initial terms of the sequence. Right? So these are the starting terms. Starting terms of the sequence. And you will have some terms in the middle. But what for the limit of a sequence, what we have to see is the very last terms of the sequence. Last terms mean n is very, 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 very large. Something like n very large from this 10 power 10 or something. So n is very, very large. So when n is that large, how will my sequence term look? Any guesses?
Sir, it goes up to 0.
It goes up to 0.
It's
Tends to 0.
almost 0, right? So when n is 10 power 10 itself, you can see that it is 1 by 10 power 10. What do I mean by 1 by 10 power 10? What will be the next term? 1 by 10 power 10 plus 1. Right? And the next term will be 1 by 10 power 10 plus 2. 1 by 10 power 10's previous term would be 1 by 10 power 10 minus 1. So in our real world, how do we treat these terms? 1 by 10 power 10, 1 by 10. So what are these terms?
We just take them as 10 power 10.
10 power minus 10, it's almost 0, right? So we
Yes, sir.
won't worry.
0.
Yeah, sir.
Yeah.
Consider them as 0.
Yeah, we will consider them as, we don't be too much accurate, right? We don't try to be too accurate. Even 1 by 10 square or 10 cube, 1 by 1000 itself, we kind of treat that 0.001 itself as 0, right? So these are very much, we will equate it to 0. Right? So all the terms, when n approaches to infinite, so this is what limit n tends to infinite an means. So when n tends to infinite, what is happening to my sequence terms? So in this particular example, all my sequence terms are becoming 0, almost 0, very, very close to 0, right? So I can say as n tends to infinite, all my terms will become 0, right? So therefore, that 0 is called as limit of sequence, okay? And this sequence is actually having the limit. Therefore, this sequence is called a convergent sequence. Okay. So if there exists a limit to a sequence, then that sequence is called a convergent sequence. Is this clear now?
Sir, I got it, but I couldn't understand that stem graph.
Okay,
Stem.
stem graph.
Sir,
Hmm.
condition of convergence sequence.
Sorry.
Condition for convergence sequence.
The condition is just limit existence. If limit exists, then that sequence is convergent. Okay.
But some limits can be 0, but the sequence is divergent.
Can you give me an example? Okay, Hari, here
Sure.
in the stem plot also, stem plot we know, right? So it is just denote, we didn't plot it as stems.
Okay.
Okay, so these dots denote the sequence term value. Okay, so that is what it means. So the first term is something minus 0.5. Okay, so the second
Okay.
term is 1.5. The third term is 0. Fourth term is 0.9. Fifth term. So this is the sequence. So it is going like that. So even in this sequence also, as you see, as n goes to 60, my term values are almost 0.5655. So it's all coming together. As n tends to 100, you can see everything became 0.51 and some terms are 0.49. As you go to n 1000, everything will be 0.5, 0.5, 0.5, 0.5. Okay.
Okay.
So that means this sequence is actually converging to 0.5. And the limit of the sequence is becoming 0.5. Okay. So that
Sir,
means this
actually,
sequence.
what is L plus limit plus 0.2
That
or
is,
L plus?
so that is what, that is little confusing. That is why I didn't bring those things. So forget about it. You don't worry about these things. Just worry that
Thank
you know the sequence and what is happening to the sequence at the end. Okay, so that's it.
Okay,
That is
I got
sufficient.
it, sir. Thank
Yeah,
you. Thank you, sir. Thank you.
yeah. So you can see here, 1 by n is given here clearly, right? So it started from 1 and slowly it, at n is equals to 20 itself, you can see, right? At n is equals to 40 also, you can see very, very close. At n is equals to 100, it's almost 0. So there is no stem at all to any value, right? So as I progress, if I take 10,000 or some number, it's almost 0. So it will just lie on the x-axis. All the terms will lie, all the points will lie on the x-axis, which is nothing but as n tends to infinite, an will go to 0. Okay, so L will become 0. That's it. Okay, and this is like a proof. So this is the mathematical way of denoting the limit of a sequence. Okay, so which, even if you don't understand, don't worry. Okay. All right. So this, I think I have discussed this. If limit exists means that capital L should be some real value. Should not be infinite or minus infinite. If that sequence has a limit, then that sequences are called convergent sequences. Okay. If it goes to infinite, so some sequences will go to infinite, right? As n increases, it will go to infinite. So that means this will diverge. So we'll say it's a divergent sequence and it diverges to plus infinite. In the same way, some sequences may go to minus infinite also. So we have seen that examples, right? So if it is going to minus infinite, then we say it's a divergent sequence that diverges to minus infinite. And sometimes this will not have any limit, or in other words, this limit n tends to infinite an will go to some L1, can go to L2 also, right? You cannot, some sequences will not go to a single real number. For example, this minus 1 whole power n, right? So if you see this minus 1 whole power n sequence, it will start from 1, minus 1, 1,
It
minus
will
1,
oscillate.
1. Yeah. So even if you go, as n increases also, as n becomes very, very large also, there also you will see this oscillation, minus 1,
We
1,
get two
minus 1,
values.
1. Yeah. So the sequence will, some terms will go to -1, some terms will go to +1. So which is like, the sequence terms will not go to the single real number. So in that cases, what we say is this particular sequence will not have any limit. Okay. So, or in any, sir, yes.
So I have a doubt regarding this. I understood the fact about that divergent and convergent sequences, but I have a doubt related to the boundedness. If we have a graph, for example, half x plus sine 50x, if that's the graph, it
Sorry.
follows an upward trend. Basically, it goes to infinity, but then it is bounded by two line equations. Is that also considered bounded or is it considered unbounded, sir?
So, what is the expression? Can you half x?
Half x plus sine 50x.
Okay.
So you get a sine wave, but it is going like with the gradient of half x. So my doubt is, like, do we consider that bounded because there's only two, like there's two lines which bound the entire function, but
But
it,
those two lines are not horizontal lines, right?
yeah, they're not horizontal, but it
Ah.
still bounds the values of the function.
No, that is not bounding means. Okay, so as I said, bounding should happen with respect to horizontal lines. So horizontal lines means it will bound. So that expression which you said, half x plus sine 50x, if I can plot it, I will just plot it. I'll plot it roughly, okay?
Okay.
So that will be somewhat like this, no?
So I just tried plotting it now. It gives a sine wave of same amplitude, but it follows the line half x. It follows that line, passes through the origin.
Passes through the origin and okay. Yeah, roughly like this only, right? So is it different from this?
Yeah, so if I'm not wrong, it's different from this. It follows the line half x, it follows the straight line half x, but it forms a sine wave on that line.
Okay. Okay. I understood what you're trying to say.
My doubt is there is one straight line which bounds the upper values, and there is one straight line that bounds the lower values. They are not horizontal lines, I understand that, sir, but they're still straight lines. Do we still call it bounded or is it unbounded, sir?
No, it's not bounded, no? So I think the graph would look.
Yeah, sir. Yeah, it looks like that.
It looks like this, no?
Yes, sir.
We don't worry about the left hand side. Okay, so if it is like this, then the bounding is happening like by these two lines, no?
Yes, sir. Yeah.
But even those two lines are going to infinity, right?
Yeah, so the lines tend to infinity, but at a particular point, the graph can only have a range of values, right?
That is range. So that range is different from this boundedness. So bounded means, can I draw two parallel lines with respect to x-axis such that my plot will not go above or below that? So can I come up with this line such that this won't cross?
It's not possible.
It's not possible. So it's not bounded actually.
Okay, sir. I got it. Thank you, sir.
Yeah, right. And it's
So
divergent.
sorry,
Yes.
so the graph of sin x is bounded to 1 to -1. Isn't it, sir?
Correct. So sin x is bounded. This is bounded. But since you are adding this half x, this spoils the party. Right? So half x is not bounded. So as x increases, half x will go to infinite. Right? As x tends to infinite, half x will also go to infinite. So this is not bounded. So once this is not bounded, the sum will also not get bounded. Okay? I hope this is okay.
Yes, sir. Thank you, sir.
Right. All right. Any other doubts? Shall we move? All right. So there are many
Yes.
examples.
Diverse always remains to minus infinity instead of
Uh,
plus infinity.
Plus infinity and minus infinity, both we will call it as divergent sequences.
Okay, sir.
Okay. Yeah. So there are examples here. You can see again. So it's a constant sequence 1, right? So that is, even though as n tends to infinite, all my terms will become 1. It's a convergent sequence. So 1 by n we just saw, it goes to 0. Again, it is convergent. So these are the limit values. These are the classification of the sequence, whether it is convergent or divergent. An is equals to n. As n increases, my an will also go to plus infinity. Right? It is a divergent. An minus 2 power n. This one goes to minus 2, minus 4, minus 8 and so on. As n increases, this will go to minus infinite. It becomes a divergent sequence. Minus 1 whole power n. Just now we saw. Minus 1, 1, minus 1, 1. It is like an oscillating between minus 1 and 1. Therefore, as n increases, it will not go to a single real number. Therefore, there is no limit existence. Has no limit, we'll say. Okay. Or we'll say it is not convergent sequence. Right. Again, the last example also, it is oscillating, also increasing. Right? Increasing by amplitude. Minus 2, 4, minus 8, 16 and so on. So some terms will go to minus infinite. Some terms will go to plus infinite. Right. As n increases. Therefore, limit will not exist. And we'll say has no limit. Okay.
Sir, can you discuss some problem related to the limit of sequence?
That we are going now. So how to compute limits is the next topic. Okay. So we just saw, given the sequence to us, we know by plotting stem plot and some observations, some intuitions, we kind of saying whether the sequence is convergent or divergent or no limit, right? But this has to be explicitly computed, mathematically computed, right? So how do we compute the limits is the question, right? So what we do, we know few things from the intuitions, right? So what we know is a constant sequence, as n tends to infinite, it will stay constant, right? So this is known to us. And this sequence we have seen explicitly 1 by n, 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5 and so on. That will go to 0. So these two things are known to us. Then what we can use is, we can use the properties of or rules of combining these limits. What we do is, if I have any sequence of this kind, c times an, some constant getting multiplied to the sequence an, then you can pull out that constant c out and it will just become limit n tends to infinite an. Okay, so c times limit n tends to infinite an. So it's just a scaling. And you can add two sequences and compute its limit, which will be equals to adding the limits of the two different sequences. Okay, subtraction also holds true. Right, so these are some rules. And next, multiplication. When I take the product of these two sequence terms, an into bn, it will just become the individual product. When I take the power of each and every term, the limit will just become limit of the earlier an sequence whole to the power k. And k can be any positive value. Okay. And the division also, if I take the division between two terms, an and bn, and compute the limit n tends to infinite, it is same as computing limit n tends to infinity an and limit n tends to infinity bn, and take the ratio of these two things. Okay, and one care you should take care is denominator should not be equals to 0. Okay, and yeah, there are some more carefulness required when we are dealing with infinity 0 kind of cases. Yes. Any doubt? Rama Prasad Ghosh. Can you unmute? If you have any doubt. Okay, fine.
Sir,
Okay.
excuse me. Sir, So, can we have this lesson as a recorded one?
This is being streamed actually, YouTube streamed, and link is also available.
So where do we see
It's in the calendar only.
calendar?
Yeah.
For all courses.
For math, I pinned.
Sir, can you hear me?
Yes.
Yes, sir, I have one very interesting example. Say minus 1 to the power n is equal to minus 1 to the power n by 2 to the power n. This is an oscillatory sequence, but it has a limit. As n tends to infinity, it becomes 0.
Yeah, it's an oscillating sequence, but the oscillating
Yeah,
sequence
this is
that
an
I
oscillating sequence, but it has limit at n tends to infinity. Since
right.
the denominator is more than 1, denominator
Mm-hmm.
is more than 1 and it goes to infinity.
It Yeah, denominator goes to infinity and it comes to 0. So the
0.
for this limit exists,
Huh.
limit will be 0. So, since
Yes,
limit
sir.
is existing, this is a convergent sequence.
This is a convergent sequence. Yes, sir.
Correct.
Thank you, sir. Thank you, sir.
Yeah. So it's a convergent sequence. Yeah. Nice example. Okay. So did I say that oscillating sequences doesn't have limit? I didn't. I don't think so, right? So the oscillating sequence that we took was this. So this sequence doesn't have limit. Okay. So let's do some examples. If you have any examples that you have encountered so far while you prepare the sequence and limits, you can give me, or else we'll do these examples. Okay. So yeah. So let's do this. So mostly you will encounter these kind of problems, right? So an is given to be some 3 n power 4 plus 5 n cube plus 6n square minus 3n plus 2 divided by 6n power 4 plus 3. So when you have this big expressions, okay, and you have to find the limit of this sequence, there is a very easy shortcut that you can follow. I think most of you know this.
Taking highest power in the as common in the numerator and denominator.
Correct. So see what is the highest power in the numerator and denominator first. Okay, so the highest power is 4 in the numerator and 4 in the denominator. If the highest powers in the numerator and denominator are the same, then what you do is for limit of the sequence, you take the coefficient of highest power divided by highest power in numerator divided by coefficient of highest power in denominator. Okay, so all you have to do is this. You don't have to worry about what is coming later. Okay, so these are all useless terms. All you have to do is take the highest power coefficient in the numerator, which is 3 here, right? And take the highest powers coefficient in the denominator, which is 6, which will become 3 by 6. Half is the limit. Okay. What if? So that is one case. What if an is like this: n power 4 plus 6n cube plus 3n minus 2 divided by n square minus 4. Okay, where your numerator power is more, highest power in the numerator is 4, and the highest power in the denominator is 2, and 4 is greater than 2. So your numerator polynomial has higher degree. So in that case, what will happen?
Sir, we have to divide by n square by whole equation.
So,
So you can do
well,
that and
well,
all.
basically, we can consider it as n power 4 by n power 2, which is n square, and then that will let into infinity.
Yes, sir. By
Correct.
that also we
Diverges
can
to it.
consider.
Correct. So all you have to do is you just look at if the numerator power is more, you look at the coefficient sign, not even whatever the value is. If the sign is positive, then it goes to plus infinite. If the sign is negative, then it goes to minus infinite. So this will, I'll just put some C. Okay. So C times. So this will be infinite if C is greater than 0, and this will be minus infinite if C is less than 0. So if your numerator has more power, all you have to check is the sign of the highest power's coefficient in the numerator. That's it. Don't bother about denominator also. Okay. So what if your an has like this? Numerator has n square and the denominator has n cube. Again, c times n cube minus n square, something. Okay. Where your denominator's power is more than numerator's highest power. In that case, what do you think will happen?
0.
0.
It will be
And
0.
here we are lucky, for all C, it will be 0. So even C is positive or negative or whatever it is, the denominator dominates the numerator and it will eventually goes to 0. So all the terms as n tends to infinite will go to 0. Okay, so that way you can decide.
Sir?
Hmm.
So I have a
Yes.
doubt. What would be the limit if we take a function like, for example, nth root of n?
Nth root of n.
Yeah, sir.
That's really an interesting question, but I don't think we.
Would we have questions like similar to that? If not, there's no need to do it, sir. If it, I just want to know like if we would have questions like that.
Our question paper will not contain this difficulty, but you will see very minimal. Okay, so even n power 1 by n is also okay to visualize, right? So n power 1 by n, as n tends to infinite, what will happen?
It will be 1. Yes.
It will be 1.
Yeah. N into n power of 100. So assume that it will be 1.
Okay, 1 by n ln n e power n. So you have to do in this way, and then we have
Sir,
to
I
observe.
think
So
it will be 0. So let's suppose we take n is equal to 100, then 100 to power 1 by 100 is tending to 0. And when the increases the number, suppose n is 1000, then 1000 to power 1 by 1000, and literally them touches the 0. So if take infinity, we go with infinity, infinity to power 1 infinity, I think it might be tends to 0.
okay, okay. I
Assume
okay.
that n
Anyway,
is equal to 10, and
hmm.
so 10 into the power of 1 by 10. Then 1 by 10 will be 0. So 10 power 10 is 1 again.
I think
10 power
it will
0.
be 1.
Yeah,
Yeah,
it will
yeah.
be 1. Yeah.
It
So
will be
if we
1.
don't get this kind of difficulty, it's fine, sir. We don't need to solve it. I just
We don't
wanted to
need to
know.
solve it, right?
Yeah, sir. In case we get this, what do we do? That's all I wanted to know.
So this
If
is
it's
what
not
you
like
should do.
that,
For
no
that,
issue.
see, for that you need this exponential knowledge. Okay, so you see, right, how I am converting this.
Yeah, sir. Yeah, sir. I can see.
So I'm taking e power ln, so that this will become like this, and then I have to use L'Hopital. If I use L'Hopital, I will have 1 by x. As x tends to infinite, 1 by x becomes 0. E power 0 will become 1. So this will go to 1.
Go to one. Okay, sir.
Yeah.
Thank you, sir.
Yeah, yeah. But you may not expect that difficulty level.
Okay, so no worries. If it's
Okay.
not there, then it's fine, sir. I just wanted to know.
Yeah, yeah.
Thank you, sir.
Yeah. So that is what that is about computing limits. We will use these ideas of combining, scaling, multiplication, powers, and all to compute more limits. Okay. And the final part of week 3, maybe after this week 3 at 11:15, we will take a small break of 5 minutes. Week 4 is all about limit and continuity of function. Okay, so nothing beyond that. So don't bother too much about anything other concepts. Okay, so all we will do is that I think I will try to finish it in half an hour. Okay, so all we need to understand is how to compute left hand limit, how to compute right hand limit, how do I compute the limit at a particular point, and how do I comment on the continuity, whether it is continuous or not continuous. So if at all it is continuous, what are the conditions? If at all limit exists, what are the conditions? That's it. Okay. So we'll do that within half an hour. But let us spend some 5 minutes on this monotone convergence theorem. Again, here also I'll give you some shortcuts. Okay. So don't bother too much about the math behind this monotone convergence theorem. But we should all understand how to use this MCT. That's it. Okay. So this MCT helps us to compute the limits of some recursive sequence relations. Okay, so what does this MCT says is any non-decreasing sequence that is bounded above has a limit, and any non-increasing sequence that is bounded below has a limit. Okay, so graphically, again, visualizing is very, very important. What this means is any non-decreasing sequence means either the sequence should increase or it should stay constant. So our sequence may be like this. Okay. So some terms can be equal also. Some terms can either it should increase or it should stay constant. That is a non-decreasing sequence. So if I have any non-decreasing sequence that is bounded above, so you know that the sequence is bounded above also. So bounded above means there exists a horizontal line where none of my stems of my sequence goes above that. Right. So there is one condition that the sequence is a non-decreasing sequence. That means either it should increase or stay constant. So increase, stay constant, but you should not cross this black line. What does it imply? Increase, constant. If I keep on increasing, I will cross that black line. So I can't increase as n tends to infinite, right? So because I said I was given that it is bounded above. Also, it is said that it is a non-decreasing. So that means the sequence can increase and stay constant, increase, stay constant. Even though it increases, it should not increase like with huge differences, right? So what does it imply slowly is this sequence will eventually converge to one value. That is nothing but saying the sequence actually has a limit. Okay, so that is what MCT says. In the other statement is also the same, but in the other direction. So what does the state is? If I have a non-increasing sequence, again, non-increasing means either it should decrease or it should stay constant. So something like this. Okay, so either it should decrease or it should stay constant. Also, a non-increasing sequence that is bounded below. So if it is bounded below, that means I will have some horizontal line such that none of my stems heights, right? So this thing, these dots go below that black line. Okay, so it should not go below that black line. So all these dots should lie on above. But again, what does this imply? The sequence is going like this, but it can't go below this. So that means somewhere it has to converge above this black line. So that is what limit existence phase. All right, so this is what MCT says. So if you have these kind of sequences, limit will exist, definitely exist. Okay, and where do we use this is what we need, right? So limits like this. So if I have to compute limits of r per n, where r is less than 1. Okay, so you see that the sequence is basically 1 r, r square, r cube. It's a geometric sequence, right? And the first term is 1. The second term is r, which is less than 1. The third term is r square, which is less than r. Right? So this is a decreasing sequence. But again, since r is a positive value, right? So none of my terms will go below 0. Right? So this is a decreasing sequence. Decreasing, and it is lower bounded by 0. Right? So that means it is bounded below also. Using MCT, what we can conclude is this particular sequence has a limit. And we will say that let that limit be capital L. Now we have the recurrence relation between the next term and the current term. So I can write the geometric series as like this, right? So the next term in my sequence is basically r multiplied to the previous term. So that is what it is. Now as and I take limits on both sides. So if I take limit on both sides, I will have this expression. And I know as n tends to infinite, an plus 1 and an both will be equals to capital L, because MCT says that limit will exist. As n tends to infinite, all the terms are equal. So I will replace this and this with L. So L is equals to R times L. So this will only be, R is positive. This will only be true when L becomes 0. Okay. So that means L, the limit value is L. L, which is 0. So the limit of this sequence is 0. So this is how we can compute. And very nice example to understand this MCT better is this root 2 sequence. How do I understand this? I have a naught to be 2. An plus 1 is given in terms of an, right? So these two things are available to us. And it is also known that it is monotonic and bounded. Okay, so once it is bounded above and below. Okay, if it is monotonic, that means even though it is increasing or decreasing, since the sequence is bounded, right? Even though it is increasing or decreasing, limit should exist because it is bounded from above as well as bounded from below. Right? So therefore, by MCT, limit will exist, and we will take limit n tends to infinite an as capital L. Right now, what we do is we take this recursive relation and we take limit n tends to infinity on both sides. Okay, so when I take in that way, I will get this expression. Now I will replace L in place of this limit n tends to infinite an plus 1 and as well as limit n tends to infinite an. Because as n tends to infinite, both an plus 1 and an are equals to L. Right, so wherever I see these things, I will replace it with L. So the expression will now become L is equals to L by 2 plus 1 by L. And if I bring this L by 2 over to the left hand side, I will have L by L minus L by 2, which will be L by 2. L by 2 is equals to 1 by L. Bringing L terms on one side and the other terms on the other side, I will have L square is equals to 2. So from this, I will get L is equals to square root 2. So that means the limit of this particular sequence defined like this is actually root 2. Okay. So this is where MCT helps us. And there are many examples. Maybe I suggest you all try these examples. I think professor also mentioned this. And solve examples related to recursive relation plus MCT usage. Right. So, and I think even in graded assignment also we have some examples, right? So something like A1 is given to us, 6 or something, and then an plus 1 is given to us as something like 4.
I think an plus 1.
An plus 1 is square root 12 plus an. Okay, so something like this. So if you see like this, right, so how do I compute the limit? Right, so limit n tends to infinite, an we want. So what you have to do is, if they ask you to compute limit, it is evident that limit exists, right? So that's the general way of proceeding, right? So once limit exists, that means you have to use MCT somehow, right? If I have to use MCT somehow, all I have to do is take this recursive relation, take limit on both sides. I'll have limit n tends to infinity an plus 1 is equals to square root 12 plus limit n tends to infinity an. Right, so it is actually limit n tends to infinite out the whole thing. It is nothing but you can take that limit inside also. Okay, so this becomes L, this becomes L. So L is equals to square root 12 plus L. Now L square is equals to 12 plus L. Now we have to use the knowledge of weak one. So it's a quadratic equation in terms of L, right? So L square minus L minus 12 is equals to 0. Now we will see that I will leave it to you guys. This will be minus
4
3
and 3.
or
Yes.
minus 3. And you can clearly see that L is equals to minus 3 will not be possible, because you can see A1 is 2. And once you look at the first 2, 3 terms, you will see that the sequence will be increasing. Okay. Increasing, and also in the other way to look at is, the sequence is what is the sequence? It is an plus 1 the square root of 12 plus an. So once you see square root, none of your terms are negative. So all your terms are positive actually. So all positive terms going to minus 3 is not possible. No? So in that way also L is equals to minus 3 is not possible. Okay. So L is equals to 4. So this is how we compute limit of a sequence defined through recursive relations using monotone convergence theorem. Okay. So with that, I think we kind of finished week 3. And week 3 has more contents, right? So that it requires some time to prepare. So practice more and more problems on this week 3. Yes.
Sir, may I please have the link of today's video and yesterday's video?
It's available in the calendar.
Sir, in fact, due to some issue, I can't access the calendar. I could not.
Okay, maybe I will paste today's link again in the chat.
Yes, sir.
Yesterday's I will give it at the end. Okay. I'll have to
Okay, sir.
go
Please,
back and
please, sir.
open the calendar and give it.
Please, sir.
Okay. So let's take a short break, very short break, like 2 to 3 minutes. Okay. So just refresh yourselves and we'll start with week 4. And week 4, as I said, we are not going to spend too much time on covering all the details. We will just see how to compute left limit, right limit, and how to compute limit of a function. And then we will end with continuity conditions. Yes.
Sir, during the qualifier exam, will we have fill in the blanks type of questions?
Yes, yes. Fill in the blank mean NAT, numerical type question.
Yes, sir,
Which you
numerical
have
type.
seen in, yeah, there will be numerical type questions also. There will be MCQs also, there will be numerical type questions also.
So totally how many questions?
It will come out to be some 15, 16 questions approx.
Sir, can you tell how many marks for each subject, each course?
Each course depends on the course. At least for math, it is 40 marks. Paper is designed for 40 marks. And we will
Okay.
scale it to 100.
Okay, sir.
Okay, so let
Excuse me, sir.
yeah. Yes.
Sir, the main qualifier exam is like similar to the mock test, right?
Not very much similar, but you can expect some questions from mock test also.
No, no, sir. I mean the pattern.
Pattern will be the same.
Okay.
Even the difficulty level will also be the same. So you'll
Okay.
see some difficult questions and some easy questions in mock, right? So in the
Yes.
same way, you'll see easy and difficult.
Okay, sir. Thank you.
Okay. So let me also have a small sip of water and come back. Okay. All right. So let's resume. Okay. So in week 4, mostly we'll have to focus on this page mainly. So what is the limit of a function and what is continuity mean? Okay. So for that, we will better understand from this particular slide. Okay. So function means there exists a domain as well as a codomain. Right. So there are two things. So one is an input, one is an output. And I can plot functions on xy plane where x-axis is the input and y-axis is the output. Right now, if I have to talk about limit of a function at a particular point. Okay, so let's say x is equals to x naught. So at x is equals to x naught, I will say the limit exists if I consider any sequence on x-axis that converges to this x naught. Right, so I start from some point here and then I will move towards x naught. Okay, so each step I take is my sequence terms. Okay, so as I move towards x naught, how is my function behaving? Okay, so that is from the left side. If I start towards x naught, how are my function values are moving? Okay, so I move on x-axis and I observe how the function values are moving on the y-axis. So function values lie on y-axis, right? So if I start from left side and move towards x naught, and this is how my function values move, right? So slowly, the function value is this, and the next step the function value will be this. Next step the function value will be this. Slowly, as I move towards x naught, the function value approaches to this f of x naught, right? So that I will capture. Similarly, I will now walk from the right hand side towards x naught. Okay, and again I will capture the function values. So there are many points. So I will see the function values at those points. How are they behaving? Okay, so this becomes a sequence. This also becomes a sequence, right? So I will capture, and again, once I reach x naught from the right hand side, I will see where am I reaching on the function, right? On the curve. Okay, so one value is called the left hand limit and the other value is called the right hand limit, right? So if I start from left hand side, and move towards x0, whatever the value I get, okay, that is called the left hand limit. What if I start from the right hand side and move towards x0, whatever the value I get with respect to function, that is called the right hand. If these two are equal, then I say limit exists. If these two are not equal, then I say limit will not exist. Okay. Any difficulty in understanding this?
Sir?
Yes.
Sir, I can't understand, sir. So can you repeat, please?
Okay. Okay, so let me take a single function. Okay, so let's say I have a function like this. Okay. So we know how to plot a function, right? So that's not what we are interested in. So all we are interested in computing limit of a function at a point. So limit of a function always talks about at a point. Okay, so now my interest point is this. So let's say this is point x0. Okay, so now I wanted to conclude whether limit exists at x is equals to x0 or not. Okay, so for that, what I will do is I will consider sequences that converges to x0. Okay, so I will consider this sequence. This is a sequence. This is a sequence, right? So I can construct or consider a sequence that actually converges to x0. So I will take the x values such that slowly it will move towards x0. So that is what this x tends to x0 means, right? So what happens to f of x? Right. So as I move my x values towards x0, what is happening to f of x? That is what limit of a function means. Is it coming towards a value L, some value L, or is it going somewhere else? Okay. So if it is coming to a single value L, then the limit of a function exists at x is equals to x0. If it is not coming towards a single value L, then the limit will not exist. So for computing this limit, what we do is, the easiest way to do is compute the left hand limit and the right hand limit. Now what is left hand limit? Left hand limit
The
means
value which
is
converges from left hand side.
correct. So instead of considering any sequence, any random sequence that converges to x0, now I will consider only those sequences that converges to x0 from the left hand side. Okay, so your starting term should be somewhere here, and then the next term should be here, and then next, and slowly it should converge to x0 from the left side. The denotion for that is limit x tends to x0 minus. So minus means from the left hand side it is coming. So we will compute this. So what is happening to f of x? Let's say this will definitely be equals to some L1, some L1. Okay. And similarly, I will compute right hand limit. Okay. So right hand limit now is, again, instead of considering any random sequence that converges to x0, I will consider only those sequences that start from the right side of x0 and slowly. So x is these are points. Okay, so these are the term values. So I will start somewhere here and I will slowly come towards and converge to x0. I should not go this side. So I should consider a sequence such that it will converge at x0. Okay, but from the right hand side. So that is what right hand limit means. So what will happen to the function? So f of x, and this might be some L2. Okay, so if it is like this, I will say limit of the function exists at x0 only if limit exists if this L1 is equals to L2. So your left hand side limit should be equals to the right hand side limit. So here in this graph, you can see at x0, even if you come from the left hand side or the right hand side, your function values will approach towards this point only. Right, so a single point, and this is f of x0. Right, so this is f of x0. Right, so at x0 there exists a limit, whereas if you see this point, let's label this point as x1. Okay, so now again you have to do the same thing. You should start from the left side of x1 and move towards x1 and see how the function values are behaving. Okay, so if you see here, you will see that if you start from the left hand side, my function will slowly start approaching to this point. Right, so this point, let us label that. So from the left hand side, it will approach to this point. Whereas if you see from the right hand side, if I approach from the right hand side, right, so x1 is here. So if I approach towards x1, converge towards x1, from the right hand side, the function values will be like this, and you will see that it will slowly start approaching to this point. Right, so this point, if I come from the right side. So here you can clearly see that this yellow point and this yellow point are two different values. Right, so therefore limit will not exist at this particular point, and this is called a jump happened to the function. So there is a break to the function. Okay, so that is clearly shown here. So there is a jump at x0. It says that limit will not exist at x0. Yes.
Sir, I have a doubt in this.
Yes.
Like wherever it is discontinuous, there is no limit, right?
There is no limit. Yes.
Okay. Sir.
Yeah. So sometimes what
Well,
happens? Yes.
while calculating the limit of the function,
Huh.
we check left hand limit is equal to right hand limit. When left hand limit is equal to right hand limit, but it is not equal to f of x, then also limit will exist.
Then also limit will exist. That is the next step that we are going to see. Okay.
Okay, sir.
Okay. So here also you can clearly see that at this point limit will not exist. Okay. So here let's say open circle and let's put a function value at x3 here. Okay, so whenever you see this open or not filled circle, so it means that the function value is not at this point and the function value is at this solid point. Okay, so that is what this solid and hollow circles mean. So hollow circle means function at x3, this is not the value, this is the value. Okay, so this is f of x3.
Sir, Sir, I have a question. Do we always have to check for LHL and RHL, or in some cases we can directly put the limit value into the function?
It's a good practice to check left hand limit and right hand limit separately. So whenever we say limit, compute limit, it is always asking you to compute the left hand limit and the right hand limit. So that's the best practice. Okay.
Okay.
Yeah. Okay. So here at x3 you can see, if you start from left hand side, you will slowly start approaching to this point. Even from the right hand side also, you will approach to this open circle. Okay, so since your left hand side and right hand side are equal, limit exists at x3. Okay, so limit exists at x0, limit does not exist at x1, limit does not exist at x2, but limit exists at x3. Okay, any doubt so far in, we'll get to how to compute these limits and all, but from the graph
There are no doubts.
No doubt, sir.
perspective, yeah, limit is clear, no? Now a slight extension or added condition to,
Excuse me, sir. Actually,
yes, yes.
can you go a little up x3? Yeah, at x3. So you said it is a dot circle is a f of x, right? But it's a hollow circle we should not consider, right?
We
How
should
it is?
not consider the function value. So left of x3 and right of x3, these are the function values. But at x3, at exactly at x3, this is not the value, this is the value. Only at that point, the
Okay.
value, function value is different.
Yeah.
Okay.
Sure, sir. Sure, sir.
Yeah, yeah. So this is not always equals to f of x naught. So that also we should keep in mind. Okay. So this is a limit. So x tending to x naught and x equal to x naught are two different things. I hope all of you are
Yes.
aware of it, right? So
Yes, sir.
so limit, sorry, x tending to x naught and x equals to x naught. So these are two different things. Don't get confused. So this is like x is approaching to x naught but is not equal to x naught. So x is very close to x naught. X is equals to x naught is exactly saying that x takes value x naught. Okay, so that's the difference. So there is a
That's
difference.
absolutely equal to x naught.
Yes, correct. So yeah. So for continuity, there is an added condition that this capital L, the limit value that we are computing, should be equals to f of x naught. Okay, so the function value. So if it is equals to the function value, then function is said to be continuous. So in our childhood also, we used to determine continuity based on the graph, right? So if you lift your pen, if you can draw the curve without lifting the pen, that particular curve is a continuous curve. If you have to lift your pen somewhere in between, then the curve breaks, right? So there is a discontinuity. So you can't continuously draw the curve. So here also in this case, I can draw without lifting my pen till here. But once I reach here, I definitely have to lift my pen and then put my pen back onto the paper here, right? So there is a discontinuity. And again, till here, I don't have to move my pen, remove my pen from the paper. But at this point, again, I have to lift my pen and keep my pen back here. Again, I can draw till here, but at this point, I have to lift my pen, denote this, or plot the point this, and then come back. So I cannot draw a direct line, right? So it implies that the function value is this. So wherever I lift my pen, there the function is discontinuous. Okay. So here in this case, at x0, the function is continuous. At x1, I have to lift my pen. So it's discontinuous. At x2 also, it's discontinuous. There is a jump. At x3 also, unfortunately, even though the limit exists, the function is discontinuous. And mathematically also, you can see the left hand limit and the right hand limit are approaching to this point, and this is not equals to the function value. So these are two different things, right? Therefore, at x3 also, it is discontinuous. Okay, so we can see points where limit exists as well as continuous, right? So that is x naught, right? So if limit exists and continuous, this is how your graph will be. There will be a smoothness, right? So it will be like this. You can draw it. But we have seen cases where limit exists, but it is not continuous. Yes, any doubt?
Sir, excuse me.
Hmm.
Sir, at the point of x3, actually limit exists, but it is not a continuity.
Correct. Sorry?
Sir, can you explain it once more?
Limit exists, but does not continuity.
It's not continuous. Why? Because the left hand limit and the right hand limit are equal. Therefore, limit exists. So your L1 and L2 are same. Therefore, limit exists. But for continuity, this L1 and L2 should be equals to the function value. So at f of x3 is this, right? This is f of x3, no?
Yes.
But limit value is this, no? These are two different things. Our limit
Since
value
these
is
are
not
not
equal.
the same, since these are not same, it is a discontinuous.
It is discontinuous. Right?
Okay, sir. I got it.
I have a doubt.
Yes.
We can see that it's a hollow dot, meaning that f of x3 does not have a value at that point, right?
Correct.
But then how can it be? We said it is continuous, right?
No, it is not continuous. At x3, it is
not
not continuous.
continuous.
Yeah, it is not continuous.
That's because that particular value is neither attained by the left side or by the right side.
Not neither. It should attain from both sides. First
But
of all,
it does
limit
not
should
attain, right? Because it's a hollow dot, meaning there's no value that reaches that point.
Correct. So left hand limit and right hand limit both are reaching to this point, making the limit existence. Limit will exist because both the left hand limit and right hand limit are approaching to the same value. Okay?
That's what I don't understand. So we say that it is reaching that point, but the left hand limit will be like a very small amount before that point. The right hand limit will be a very small amount after that point.
But see, that is what
reach that point.
So it will not absolutely reach that point. So that is what limits mean is, right? So 1 by n. What is the limit of 1 by n? We say it is 0.
It approaches 0.
It approaches 0 and limit. So that is what we write, right? So that is how we define, right? Limit n tends to infinite 1 by n. We say it is equals to 0. So that is what limits mean.
Okay, got it. But because in this case we say it is n tends to infinity, but here we can't say n tends to infinity, right? Because we are pointing at a specific point.
Here we are saying x tends to x naught, no? The same thing. So n tends to infinity, x also tending to x naught.
Okay, sir, got it. Yeah, got it.
Okay, so it will go towards x naught and we compute the limit.
Okay, sir, got it. Thank you.
Got it? Yeah. All right. So we see cases where limit exists and it will be continuous. And we see cases where limit exists but not continuous. And we can see cases where both limit and continuity will not exist at all. But you should observe that we will not see any case where it is continuous but not limit, but limit does not exist, right? So is there any case such that it is continuous at that point but limit does not exist?
No, sir, it's not possible.
It's not possible because continuity means first of all limit should exist. Okay, so this should exist first, only then after continuity comes. Okay, so that means if there is limit, it is not guaranteed that it is continuous, but we can say if it is continuous, limit will definitely exist. Yes.
So just one point. What would happen for a square wave?
Sorry?
For a square wave. square wave. Square wave. When you are just considering the points that there are two hollow points at the, and you are just considering that the jump discontinuity is there.
Yes.
So there should be some points like x2 here, x2 here. So we are considering that the dotted line must be a solid line. That is my humble suggestion.
Sorry. The dotted line.
Dotted line for the square wave. The here the point is like x2 situation, x2, x2.
Okay.
In the given
X2.
graph, it is just like x2, point x2.
Yeah.
x2, and if we consider the square wave, these x2 like situations are just prevailing everywhere. Okay, and then we are just considering the jump discontinuity, that is the dotted line at x2 that must be replaced by a solid line, and we are just considering it as a uh, continuous region, not discontinuous. This is my humble suggestion because this is mathematics related to electronics. That's why, sir.
So you are saying it should be like a dotted here or above? Sorry, I missed at the end.
Yes, sir. At x2 point, we are just considering a vertical gap. The vertical gap is represented by a dotted line. Yes, sir.
Correct.
And for the square wave, or the some prevailing examples in electronic science, these are
Yeah.
very common. These are very
Correct.
common, like
We will
square
just
wave.
draw
Yes,
it
sir.
like a straight line. Correct. Okay. Okay. Can we move forward?
Yes, sir.
Please, sir. Please, sir.
Yeah. Thanks. Sorry. All right. So that's continuity, right? So we will not encounter any case where it is continuous but limit does not exist. So we can say two statements here. One is if there is no limit, right? So if you are guaranteed that limit does not exist, that will definitely imply that it is not continuous, right? So this we can say. And the other statement is if it is continuous, contrapositive of this, if it is continuous at a point, then I can say limit should definitely exist.
Sir, sorry to interrupt. To answer this Rama Prasad question, right? So there in the week 3, right, we have the difference. Like there is a limit -1 and +1, -1, +1, right? So the square waves will be like it is a -1, +1, -1 and +1. So if it is that, right, it has no limit, right? So if you correlate with that statement, right, so the square wave function doesn't have the limit. In the week 3 it starts, yeah, it's a
Okay.
-1
Now I
+1
understood.
-1
Okay.
+1, yeah.
Yeah. Oh, all right.
So the limits
Yes.
will be occur for the sine waves or yeah, yes.
Correct. All right. Thanks.
Yeah, welcome, sir.
Yeah. Okay. So this is very important because sometimes in questions, no, we'll just say function is continuous at x is equals to 2. So if we say continuous, what does it mean? it means that this condition is satisfied. So limit extends to f of x
is
is
equals to f
f
of
of
t.
2. And not only that, this limit extends to 2, f of x exists. Okay, so this exists. This exists means the left hand limit is equals to the right hand limit is equals to the function value. So whenever we say continuous, this is what we mean. Okay, so I think there are a couple of examples in the graded assignment also, right? So suppose f of x is given to you with some constants, unknown constants, and we just said f of x is continuous at x is equals to 2. So then all you have to do is use these conditions and find those unknowns. Okay, so yeah, I think these are the major concepts that you have to focus on week 4. How to compute the left hand limit, how to compute the right hand limit, and whenever we say it is continuous, what are the different conditions that you have to consider or taken into consideration to solve the problem. Okay, so this is called jump discontinuity, where the function jumps suddenly, right? So this is called jump discontinuity. There is another discontinuity which I have shown, which is called removable discontinuity. So what we do is, at one particular point, we will just remove the value of it and keep at some other place. So something like at x3 point. Right. So here you can see at x3, left of x3 and right of x3 are all continuous. At x3, what we did is we removed this point and put it at somewhere, some other place. Right. So that kind of discontinuity is called removable discontinuity. These kind of discontinuities are called jump discontinuity. Okay. Yes. Any doubt? Ramaprasad, any doubt?
Yes, sir. I had just one humble question regarding the links up to today's lecture and yesterday's. And it is a very, very exciting and very high quality lecture. Thank you, sir.
Okay, I pasted it in the chat. You can get it in the chat.
Okay, sir.
So I
Please,
think
sir.
I pasted today's lecture, and
Yes,
Amit
sir.
has pasted yesterday's link. So you can go through.
Sir, in fact, I can't access the calendar, academic calendar, so it is not
I
accessible to me.
think from the portal you
Yeah.
can click on important links, and in that you will see calendar,
A
course
calendar I
calendar.
cannot access for some issue. Yeah, it is not possible for me. I tried several times.
Oh, is that so? Then can you mail?
Sir,
Not now, maybe.
if you can kindly just write down the same on the board, then we can just have it, the links, or just paste it.
I pasted it already, so you
Okay,
can
sir,
get it.
please.
Yeah,
On
yeah.
the board, so we can just take the screenshot.
On the board, should I write the link?
Uh, in fact, the
Okay.
links are not available. In fact, if some of the friends can just provide me on the discussion group WhatsApp, then it will be nice. Thank you, sir.
Okay. Okay. All right. Anyway, let's come back. So these are removable discontinuities, and this is one important thing. How do we compute limits of a function, right? So for that also we have some very well-known limits. If it is a constant function, then the limit value will always be c, right? And if it is a function like this, f of x is equals to x, then it will just be x naught, right? So any sequence that converges to x naught, here also function sequence will also converge to x naught. Right, again, there are many rules. These are all, I think we have discussed these things in week 4, during week 4. Right. and using them we will compute these limits. Okay, so we'll do 1 or 2 examples and then you practice more. Okay, so let's solve it here itself. So you see any polynomial, we know that polynomials are continuous functions. If it is continuous function, we know that limit exists. Limit exists means left hand limit and the right hand limit are both same. So once they are all same and it is also equals to the function value, you can directly, when x tends to -2, it will just be f of -2. Right. So what I used the knowledge that I have from polynomials. Right. And yeah, examples like this. Okay. Where limit x tends to 0, 1 by x minus 1 plus 1 by x plus 1 whole divided by x. So if you see these kind of examples, no, just make sure that can you simplify it a bit. Okay. So if we can simplify this a bit, then things would be really easy. First thing, you just see whether the function is continuous or not. If it is continuous, just directly substitute the value. So that is first and easy case. And the next thing is, if you see something expressions like this where you have numerator and denominator, first and the next thing you have to do is see whether you can simplify the expression or not. Okay, simplify. Numerator looks that looks like we can simplify it. It becomes x plus 1 plus x minus 1 divided by x minus 1 into x plus 1, right, and whole divided by x. Now I can see that plus 1 minus 1 gets cancels and this will just become 2x and everything will go to the denominator, right? So again now x and x will get cancelled out and I will have expression to be 2 by x minus 1 into x plus 1, and this is the simplest thing I can do, or else I can multiply these two in the denominator also. It is a minus b into a plus b, which is a square minus b square, which is x square minus 1, right? So this is the simplest form I can get and I have to compute its limit. So limit x tends to 0, 2 by x square minus 1. So again x square minus 1 is looking like continuous. If you think it's very difficult to judge whether it is continuous or not continuous, for computing this, you compute what happens to this function when x coming from left side of 0, what will happen to this, and compute x coming from right side of 0, what will happen to this. Okay, if these two are equal, then that will be the limit value, and you can clearly see that in both the cases these two will be right. So these two things will go to -2 because either x approaches to 0 from the left side or the right side, x square will move towards 0. So 2 by 0 minus 1 is simply -2. Right. So first thing is check whether it is continuous or not. Function is continuous or not. If it is continuous, directly substitute the value. Okay. If you have the next thing, if you can't substitute the value directly, what you have to do is you try to simplify the given expression. Okay. If you simplify the given expression, then if you simplify the given expressions, then it is very easy to compute the limit. Yes.
Sir,
Doubt? Any doubt?
yeah, sir, can you please help to solve u4 minus 81, u3 minus 21?
Yeah, we'll do that.
Thanks.
Okay. So first thing is direct substitution. If you are guaranteed that the function is continuous. Okay. So in this cases like this. Next thing is simplification. And the next thing is if you can do some factorization. Okay. So again, it comes under simplification only, but it's more like you have to identify whether there exists any factors that will cancel out in the numerator and denominator. Something like what Subramanya Shiva has asked, right?
Yeah.
So
Yes.
limit u tends to 3, u power 4 minus 81 divided by u cube minus 27, right? So u power 4 minus 81, you can factorize it, right? So it looks like u square whole square minus 9 square, right? Something like a square minus b square formula. You can factorize it as u square minus 9 into u square plus 9, because a square minus b square is a minus b into a plus b, right? And the denominator also, it's a cube minus b cube formula, right? So what is a cube minus b cube? If I have to factorize it, it will just be a minus b into a square plus ab plus b square, right? So if I use that formula, I will get u minus 3 into u square plus 3u plus 9, right? Again, u square minus 9 is again, it is in the form of a square minus b square. I can further factorize it into u minus 3, u plus 3, u square plus 9 divided by u minus 3, u square plus 3u plus 9, right? And this is the possible factorization I can do in the numerator and denominator. Nothing much I can do, right? So now I can cancel these two out, right? So once I cancel these two out, what I am left with is, in the numerator, I will be left with u plus 3, u square plus 9 divided by u cube, sorry, u square, no, u square plus 3u plus 9. So now you will see that you will not face any difficulty in substituting u is equals to 3, right? Because numerator is very nice polynomial, denominator is also a nice polynomial, quadratic polynomial. When you divide these two things, you will still have some niceness, right? So there is no discontinuity or breaks you will see encounter. So this will evaluate to f of u, that is 3 plus 3 into 3 square plus 9 divided by 3 square plus 3 into 3, 9 plus 9, right? So you just have to simplify it. So if you simplify it, I think 6 into 18 divided by 18 plus 6, 24, right? So 6, am I correct? 4. Most of you are giving it as 4, but
Denominator is 27, sir.
oh, sorry, it's 3 square, no? Okay. Yeah. So it's 27. So we can 2s and 3s and 3 and 2, it will just be 4. Okay. So again, going back, if it is like this, you are guaranteed that it is continuous, substitute. If you see,
Please show me
sorry,
previous question.
this is the previous question, no?
Yes, sir.
So you want this page?
Yes, sir. Previous one.
This one?
Yes, sir. 1 minute, sir.
Okay. So look out if you can simplify it. If the expressions are looking complicated, try to simplify it. Simplification may involve like this, multiplying and some terms getting cancelled out, or it involves some factorization. Okay, so in both the cases, our expression will simplify and then try substituting the value. Okay, and cases like this is same like what we have done for sequences. Okay, so if you have same degree, numerator and denominator. Okay, so it's not infinity, no? Okay, here also the same thing. You just follow the same approach. Try to simplify the numerator and denominator. Okay, or before that, just try to substitute this value t is equals to -1 and see whether you are getting any real number or not. Okay, so if you are getting real number, then that will be the answer. If you are getting something like 1 by 0, 1 by 0 also, it's okay. But if you are getting something like 0 by 0 or infinity by infinity forms, then you have to look out for some terms will get cancelled out. For that, you have to factorize. So in this case, it turns out that if you directly substitute -1, what will happen is -1 whole square plus -3 plus 2. And the denominator is also -1 whole square minus -1 minus 2. So you'll see that the numerator will become 0 and the denominator will also become 0. So if you encounter these cases, that means the numerator or denominator both has the same factor that needs to be cancelled out. So for that, what you have to do is you have to factorize it. So for factorization, if you factorize the numerator, you will get t plus 1 into t plus 2. And the denominator, if you factorize, you will see t plus 1 into t minus 2. Okay, so you will have a same factor t plus 1 in the numerator and denominator. Cancel it out. Okay, once you cancel it out, then we will not face any difficulty in substituting -1. So just substitute -1. You will see the numerator is 1 and the denominator will be -3. Okay, so 3 simple rules. Directly substitute when you are confident that it is continuous. When you directly substitute, if you are facing any difficulties or if you are facing this 0 by 0 or infinity by infinity, then you have to simplify your expressions. Okay, so some terms will get cancelled out, then substitute it back. Okay, and the last concept, I think, limits at infinite. Even this is also slightly important, but whatever we saw limits of a sequence, no? So the same thing holds here also. So the same, something similar to that only. So what will happen to the function value as x tends to infinite, or plus infinite or minus infinite? Is it going to a single value or is it going to diverge? Okay. So here also you will use the same rules that we discussed in sequences. Here also applies the same. Okay. So solve the problems related to this limited infinity also. Yeah, that's it. That's it from week 4. And yeah, these are the things that you have to focus more on week 3 and week 4. All right. Yeah. Any doubts?
Sir, I just have one doubt. Sir, you have said one statement that a sequence of rational number can converge to an irrational number.
Correct.
So my question is the reverse is true?
Like irrational numbers converging to a rational number, is it?
Yes, sir. Sequence of irrational numbers can converge to rational number. Is it true?
True, no? So something like n power 1 by n only.
Yes, sir.
Right? It converges to
Yes, sir.
1, right?
Yes, sir.
Yeah, it can be true.
It can be true. Yes, sir. Yes,
Yeah.
sir. Thank you, sir.
Yeah. All right then. All the very best for your exam.
Hello, sir.
Hmm.
Sir, in the mock test, may I ask a question in this?
See, mock test is given for you guys to practice. Okay. So if you ask doubts in that, maybe I will not give you the complete solution. I think the answer is given to you, I guess, by now. The deadline is passed, right? You are able to see answers.
So the deadline is today.
Today at
Yes,
what
today,
time? I
night,
asked for 10
like
a.m.
10 p.m., sir.
Oh, it kept 10 p.m. Okay, sorry. So I asked for 10 a.m. only. Before this session starts, I wanted to end it. Anyway, you will get more time, no? Just try to solve it. See, mock, why I don't want to discuss is, you will encounter few questions, some sort of similar type of questions in your exam also. Okay? So just
Okay,
work
sir.
it out, no? Which question you have? Maybe I'll give you some hints.
Sir, question is, may I read this question?
Yeah, just read out, no?
Sir, once a minute. Sir, question number 13. Consider a infinite
Infinite
sequence of.
sequence of squares. Okay, I got it. Yeah. So the hint is basically you have to find a recursive relation in terms of Si plus 1 and Si. Okay. So that's the
Okay, sir.
hint. So it is given in English words. All you have to do is to convert it into math equation, math form. Okay.
Yes, sir. Is one more than half of the side length of sequence Si?
So Si plus 1 is one more than half of the side length of square Si. So if you think square side length of square Si is some A,
Yes,
what
sir.
is half of A? A by 2.
A by 2. Yes, sir.
One more than half of A. What does it mean? A by 2
One,
plus 1.
A by 2 plus 1.
Correct. So that is the side length for Si plus 1.
Yes, sir.
Okay. So that is the connection between the side length of Si
Okay.
plus 1 and side length of Si.
Okay, sir.
So once you have this, what is the maximum possible area for any square in this infinite sequence is nothing but as I tends to infinite, what will happen to this side lengths. So it's kind of like asking the limit of the recursive sequence.
Okay, sir.
Okay. Yeah. From here, I think you can solve it on your own.
Sir, question will be more MCQ type, sir.
No, MCQ and NAT. So in mock also you saw NATs, no? Both numerical type, like blank,
Yes.
fill in the blank type, as well as MCQs. Both will be there.
Okay. Okay.
Okay. All right, guys. Then thanks a lot for joining, and all the very best for your exam. And I hope.
Sir, again, I am very sorry to disturb you. The point is that I am not able to access that academic calendar. So where from I can get the links today's and yesterday's? No other lectures admitted.
Okay. So can you open the chat, today's meet chat
Yeah,
box?
meet chat in the meet chat in the WhatsApp group. I have requested everyone to just provide the link. I am yet to get any response. That's why.
No, not
If
in
anyone
WhatsApp.
can, yeah.
Not in WhatsApp. You are
Then
on the Gmeet, no? Gmeet. Now
Gmeet I
this
did not access. Yeah. Gmeet I did not access because I have some other assignments. I could not get
no,
everything. I
no,
just
now you
stopped the
joined in
gradient.
Gmeet. Sorry.
Gmeet.
You have joined the Gmeet right now wherever you
Right,
are
right, right,
attending. Uh,
right.
Now in this, can you see some chat box? Did you join with mobile or